All right, we're now recording. Let's get the slideshow set up from the current slide. And it's one of those really pathetic little slides that you can't see because I haven't put the projector on. But while that's coming up, let me go over this. I told you before about notification and application for graduation. If either of you are graduating this term, got to get that in as soon as possible. No later than the end of the month at all. Yes?
But I ended up just taking the class. I'd rather just be already done. So
Right.
I told them, like, I got my cap and gown and stuff.
Right.
Do I have to reapply for graduation?
I would go to the records office and ask them. They may be able to just pull your old one and use it. But if you didn't go through it when you applied before, they may have thought, who knows what they did with it. If they tossed it, then you have to reapply. If they put it in a holding folder, then they can probably just pull it out. So check with them and see. I don't know. Yeah, that would be a good thing to check. Graduating this spring or in the summer or this spring? Okay. Yeah, check with them and see. Otherwise, they might need it. But usually it seems like they do. It seems like I've seen them pull those out again and say, yeah, this person applied and we haven't, they didn't graduate. Do you know anything about them? So they've asked me that before, so they may actually have it there and may be able to redo, or because that thing says term graduating, that may have whatever term it was, and so they may want you to do it. But ask them. I wish I could tell you something. What's that?
Once you leave, you click on that link, and it's all you have to do, right?
Okay, for the notification, yes. For the application, you have to actually print it out, fill it out, and second?
And I turned that in where?
To the records office. Yeah. Yeah. Are you mostly on this campus or Birmingham? Birmingham. I'm sure it's the record office there too, but if you want to, you can turn it in here. Since you're on both campuses, it doesn't matter. But I know the folks here. I know some of the folks over there, and they're good people, all the ones I know. I know the ones here are really good about keeping up. So. Well, I'm sure they are. Because a lot of the times it's the same people on both campuses too. All right, so both of you are graduating this spring, is that right? Oh, really? Wow. I just found out I may not be there to watch you because if you're walking, because I have a niece and a nephew graduating this term, one at Auburn and one at LSU. And I believe the one at Auburn is the same day as this one, so we'll be down in Auburn to watch her graduate. So, what's that again? Graduation? Yeah, it's on I know it's on the syllabus. I don't have it written down anywhere where I can see it right now. But check the syllabus. I think I looked it up and put the date on there. Okay, and it's also on the Lawson State webpage under academic calendar. I know it's listed there because that's where I got it for the syllabus. Okay. So, any questions on anything up to 2.8 so far? All right, 2.9 then starts the formal definition of a limit. This book is exactly backwards from how I learned calculus way back decades ago. Boy, my professor started with this, and then we did the other things, but he started with this. And I don't particularly like starting with this, so I'm not griping about it. I'm just saying this is the way we did it before. So, the formal definition of a limit. In this section, we re-examine. Notice one of you don't have a book, so I'll go through this. We re-examine the definition of a limit in order to state it in a more rigorous and precise fashion. Why is this necessary? In section 2.2, we define the limits by saying the limit of f of x as x approaches c is L if the absolute value of f of x minus L becomes arbitrarily small when x is sufficiently close to but not equal to c. And I think I said at the time, what do these weasel words mean, arbitrarily small and sufficiently close? That's exactly what they're saying here. We must find a way to specify how close is sufficiently close. Okay? So we're going to start with this thing. Recall that the distance from f of x to L is the absolute value of f of x to L. F of x minus L. Same as we did before. So let me get my pen activated. You know, something's not working right. And I don't know what it is. Oh, I know. I do know what it is. I can't activate my pen from that module. Okay, now we can do it. All right, recall that the distance from f of x to L is the absolute value of f of x minus L. And it doesn't matter what order you do. You could L minus f of x. The absolute value takes away, this just says, tells you how close, whether you're to the left or to the right, or up or down. It doesn't matter how close they are. It is convenient to refer to the quantity as the gap between the value f of x and the limit L. Okay? Now there's a little side note here. A rigorous proof in mathematics is a proof based on complete chain of logic without any gaps or ambiguity. That's a different gap from the one we're just talking about. The formal definition of a limit is a key ingredient to rigorous proofs in calculus. A few more proofs are included in Appendix D. More complex developments can be found in textbooks on the branch of mathematics called analysis. So if you're a math major, I don't think either one of you are, that's where you would go for those. I tried to avoid those, but that's just me. Okay, I'm not a math major, I was a physics major. Okay, it is convenient to refer to that as the gap between the value of f of x and L. So let's evaluate this limit here. The limit as x approaches 0 of sine of x over x, and we know, we've already said, that's equal to 1. Okay? So this is your f of x, the sine x over x. Okay? The L is the 1. Okay? So what we're looking at is that we're trying to investigate the absolute value of the difference between sine x over x minus 1. Oops, I've just been teaching linear algebra, and you usually close off things with brackets. This is not, this is absolute value. I need a straight line here. Okay, that's what we're investigating. Okay, now we want that to go arbitrarily small when x is sufficiently close to but not equal to 0. Because you see, here x is approaching 0. Okay? So you're, now, get the big picture here. F of x, that's your y value, right? L is somewhere on the y-axis. Okay? Now, x is going close to 0. So those are dealing on the x-axis. So you want the difference between this and this to get very small the closer x goes to 0. That's what we're doing. It's basically rise over run. Okay? The rise is the difference between f of x and L. y2 and y1. And the x's, x2 to x1, minus x1, that would be your x minus 0. That's what you're doing. A slope of a tangent line, because we're letting the limit as that x and 0 get smaller and smaller and smaller, so you're giving the slope of a tangent line. Okay. Now, they're going to play around with this, and let's see if they have the next slide. Yeah, they do have them here. So let's take a look at this. Okay, back up. Okay, try this again. Here we go. Can't get all of them on, so I'll just get these two. right now. Here we know already is this graph of y is equal to sine x over x. Remember this how it is, with a hole here because you can't divide by 0. But we've already said qualitatively that as x is approaching 0, either from the left or from the right, that the function seems to be approaching 1. It doesn't equal 1, but it does seem to be approaching 1. Pretty obviously it does, okay? So here is your function. Now, you can look at that and say, yeah, I know 1 has to be the limit, okay? But what we're going to do now is say, for the difference between your f of x that you can measure. You can't measure f of x at 1 because, at 0, because that's not defined there. It's indefinite, yes. I'm blank on my terms here. It's indefinite there. It's not absolutely undefined, but it's, is that the term I think it is? Indefinite, okay, as it goes there. Looks like it does have a limit, but we don't know for sure. So the places that we can evaluate this, sine x over x would be here, here, x values right in here, and sure enough, the sine x over x is approaching 1, but it's not equal to 1. So you can't ever get that to be 0 because this is not defined at 1. It's defined right there, which is not quite 1, or over here, which is not quite 1. But the closer you get here, the closer that gets there. That's basically what the limit says. Okay? So here's what they're doing. What if they say you want this limit to be less than 0.2? How close would you need to be here? Okay? To make that less than 0.2. Okay? And then what we could do after that is zoom in on this, and this is for it to be 0.2, but now let's take this range here and blow it up over here and say, well, what if we want it to be less than 0.004? Can we get arbitrarily close, and can you always find a value that this can be to get you within this? In other words, where do you need to do to get within 0.02 here, or 0.2 here? How close do you have to be on x? Okay? It tells you here, if you get within y, you're within that. But here, if you go to 0.004 here, how close do you have to get? They said x is less than 0.15. The point being, if you want this to get arbitrarily close, 0.001, can you get within that? And the answer is yes. Okay? And that would be then constitute your formal proof. So this is how you do it sort of graphically. Let's go back and see how you actually do it. Okay? Algebraically. All right, let's see. We haven't quite gotten there yet, so let's do it this way. You want this gap, the absolute value of f of x minus 1 to be less than 0.2. So let's write that, okay? The absolute value of sine x over x minus 1 to be less than or equal to, less than. It's less than, I believe it is. Yeah, less than 2, not less than or equal to 2. So let's take off the equal sign there. Less than, what was it, 0.2. 0.2. Okay? Now, and unfortunately, all they do is use the graph. I'm sorry. They use this graph right here and say, if you want this to be less than 0.2 here, then go down and see what value creates that. They say plus or minus 1. So they then say 0 needs to be less than absolute value of x less than 1. And if you do that, you'll do that. Well, try it. Try sine of 1. Do that. And be sure you're in what mode? Radian mode. Do sine of 1 and then subtract 1 from that and see if you get less than 0.2. Negative 0.6. Ooh. Oh, 0.15. Okay, and that's less than 0.2. Yeah. Okay, you've done it. If you get within 0.1 of a 1, x less than 1, sure enough, you got your difference there. Now, what they're saying now, but what if you want it a lot closer than that? Like 0.004, how close would you have to get here? Now this time you're going to have to divide. They're suggesting that 0.15 would do. So let's try that. Sine of 0.15, again, be sure you're in radian mode, divided by 0.15, and then subtract 1 from that. Sine of 0.15 divided by 0.15, and then subtract 1 from that answer. Negative 0.3 something? Whoa. 3.3? Okay, just 1.33. No exponent out there? Okay, so that's actually further away than 1 was for you. Because of that, you got 0.15. Okay. Again, you're in degree mode. I mean, radian mode, right? Yeah. Yeah, 0.00374. That's less than 0.004. So yeah, you've done it again. Okay. That's exactly the type of thing you're doing. If you want the y value to be within a certain tolerance there, just bring in your x's until you're guaranteed to be within that tolerance.
You gotta put it in parentheses like that whole sign.
Okay. Yeah. Yeah. Okay. Do the sign. No, it's 0.15. Sign of 0.15. Yeah. 0.15 minus. No, divided by 0.15. And then, yeah, and you see, and this, yeah, you did it, and that's 0.0037. Yeah. Because you had exponent of -3. Okay. 10 to the -3. All right, so that's the type of thing we're doing here. How do we do that without numbers to get arbitrarily close? Okay. To express this in a precise fashion, we followed the time-honored tradition in using the Greek letter epsilon, small letter epsilon, and the small letter delta, okay, to denote small numbers specifying the sizes of the gap between the quantity x minus c, x minus 0, whatever it is, and f of x minus l, okay? So here's what the change we're going to do here. Instead of 0 less than or equal to absolute value x, less than or equal to, okay, I'm sorry. We're not putting the equal signs. I'm so sorry. I tend to put them in. Less than 1, except we didn't want 1. We want this to be your delta now. Okay? Then the sine of x over x minus 1, or the limit, we want that less than epsilon. In other words, the epsilon is the change of the y's. How close? What kind of tolerance? How close do you want that to be 1? You can't get it right on 1, but how close is going to be close enough for you? And if you make that arbitrarily small for epsilon, can you find a delta small enough to make that happen? We just did for the 2 they gave us there. Let's see how we do it now. This then is the formal definition of a limit. This is what we'll use not all that often. I mean, pure mathematics, they want you to use it all the time. We'll use it often enough to be comfortable with it, maybe, and then we'll go with something else, okay? Formal definition of a limit. Suppose that f of x is defined for all x's on some open interval containing the number c, but not necessarily at x equals c, okay? But it's defined for all other x's in that open interval that contains c. Then the limit as x approaches c, this value c that may not have an actual value there, but as the limit as x approaches c of f of x equal to L. That's our standard definition of a limit, okay? That limit is going to exist provided that for all epsilon greater than 0, because I can hear Dr. Osborne saying this now. He almost did it in a sing-song manner. For all epsilon greater than c, there exists some delta, epsilon greater than 0, there exists a delta also greater than 0, such that the absolute value of f of x minus L is within the tolerance of that epsilon, that very small epsilon you choose, less than epsilon, if 0 is less than the absolute value x minus c is less than delta. Now, this has always been sort of a puzzle to me of why they express this one this way and this one that way. It's just as good to put 0 less than this is less than epsilon, okay, if 0 is less than this less than delta. Or you could have just said absolute value of x minus c is less than delta, because this absolute value means it's got to be greater than 0. This absolute value means it's got to be greater than or equal to 0, but this isn't ever equal to 0, so can you get arbitrarily close? That's what we're getting at. Okay? That's your formal definition. Okay? Now, the formal definition of a limit on the side note here is often called the epsilon delta definition. Tradition of using epsilon and delta originated by the writings of Augustin Louis Cauchy. I think we ran into him earlier, but if not, here he is, okay, on calculus and analysis in the 1820s, which was considerable length of time after Newton and Leibniz came up with the concept of calculus. The actual formal definition was much, much later. The symbols epsilon and delta seem to make this definition too abstract. Keep in mind that we can use epsilon of e is epsilon equal to 10 to the minus n, delta 10 to the minus m, and therefore the limit as x approaches c of f of x equal to L. For any n, there exists some m greater than 0 such that, and then just rather than epsilons and deltas, you can put in 10 to the minus n and 10 to the minus m, I'm not sure that makes it any better, but they say if you don't like the abstract Greek letters, you don't have to. So let's do example 1 and let's see if we can do it. And of course, they start you with one that's really easy, okay? Let's let f of x equal 8x minus 3. Okay. Now, any of you want to make a guess about what the limit of this is as x approaches 3 of 8x minus 3? No, that's a plus 3. I was going to say my answer is not their answer. Okay, 8x plus 3. Sorry about that. Anyone want to hazard a guess of what that is? 27. Okay. But all of us agree. Yeah, that's the limit of it. Plug it in, it works. But how do you prove that formally? Okay. What you say is, if that limit exists, that implies there is an epsilon, or is true if and only if there is an epsilon greater than 0, such that the absolute value of f of x minus L is less than epsilon for some delta greater than 0, such that absolute 0 is less than absolute value of x minus 3 in this case, because I didn't put, they said C, but let's go on and put the 3 in there, is less than delta. Okay? That's what we're trying to get at. For any arbitrarily small epsilon, give me an epsilon, any epsilon, I don't care, as small as you want it, then I'll come up with a delta that says, yes, we can get within that. Okay? So let's do it. Well, let's start with the part we know. The absolute value of 8x plus 3 minus 27, right? Is your F minus L. We want that less than epsilon. And by the way, that's also going to be, because it's absolute value, it's going to be greater than 0. Okay? It's going to be within those, right? Well, let's actually do the math inside there. 0 less than or equal to 8x minus 24 less than epsilon. Okay? We just combine the like terms there, right? Okay. Now, what we're going to do is add 24 to all three sides. Let's see, is that right? I left off the absolute value sign there. Well, they're doing it slightly different from I did. Let me go on and do it the same way they do. They leave off this. They just investigate this argument here, remembering that's less than epsilon. Okay? So, yeah. I was jumping a little bit too far ahead. Okay. I'm going to go on and put it back in there. What can we do here? Well, we can factor out an 8. And what would that leave us with? 8 times x minus 3 less than epsilon. And this also is greater than 0. Right? Now, let's divide everything by 8. Okay? This is still 0. This is, the 8's go away. Absolute value x minus 3 less than epsilon over 8. And epsilon over 8 can become our delta then. We've done it. We found a delta such that no matter how small you choose the epsilon, how close you want to get to 3? 0.1, 0.01, 0.000001. You pick an epsilon and say, I want to get within that close, and make it as small as you want to, okay? Some finite number. Then this says whatever epsilon you choose divided by 8 and you'll have a delta that's guaranteed to make that work. So there it is. You just carried it through, and this is what we're trying to show. Okay? 0 less than or equal to this is less than or equal to delta. What delta you use? Epsilon divided by 8. So if you say I want it within 0.001, okay, we'll do it. We'll choose a delta and take your calculator to 0.001 divided by 8. If you go with that small a delta, you're guaranteed to get that epsilon within that range. So what that's saying is, no matter how small a tolerance you want to get, how close you want to go, you can find a delta that works. Okay? Now, I don't know if they're going to, they probably won't. They'll show you the rest of this, and we'll get to that. But let's say we had one of those functions like the sine of n. And we want to say, does that have a limit? Well, as long as you do the epsilon greater than 1 or even equal to 1, every one of those works because all the values of that thing are going to be between plus or minus 1. That would be fine. But if as soon as you say, no, I want that epsilon to be 0.5, you'll never be able to get 1 because those points that go like this, some of them are outside plus or minus 0.5. They're all inside plus or minus 1, but not necessarily inside this. So no, you can't ever do it that way. Okay? But if the limit does exist, you can make that epsilon just as tiny as you want, as long as you can find a delta, tiny delta, that's going to guarantee you get there, you got the limit. Okay? Now, let's look at what they're doing with that graphically. Oh, here it is. It's the same thing. I didn't know they were going to show this. For the f of x, let me blow this up. Same thing we did. Okay? This is where you start. For any epsilon greater than 0, there is such that the absolute value of your f of x minus your limit, okay, is less than epsilon if 0 is less than x going to 3, so that's your x minus 3, that's your delta x there, is less than delta. Okay? I'm using deltas in 2 different forms there. Okay? When is that true? Well, plug in what this is, 8x plus 3, wasn't it? Then add plus 3 to minus 27, you get 8x minus 24, factor out the 8, and you get x minus 3. So that means divide out the 8, and that gives you, for any epsilon you choose, divided by 8, that'll give you a delta. Now that's for this problem. Other problems, sometimes the delta may be bigger than the epsilon. This time it's less than the epsilon. Doesn't matter. It's some relationship to the epsilon. Okay. Now what does that mean graphically? Here's what it looks like graphically. And frankly, I can remember when I was first quarter freshman, I went to Georgia Tech and had Dr. Osborne for my calculus. He was an excellent instructor, professor, but my goodness, he moved so fast and he went so deep. I mean, I was just hanging on by the fingernails. I'd never had any pre-calculus in high school. It jumped right into calculus in college. I mean, there wasn't any pre-calculus they offered there. And I was just barely hanging on. I was just kind of memorizing things, not knowing what it meant. It was only when I sat down to study with my roommate and some of his fraternity brothers for the final exam, because it was going to be a departmental final exam. And I went back and they'd start to do a problem and say, I remember Dr. Osborne did something like that. I went back, and then when I looked at his notes at the end of the term, they made perfect sense, okay? When we were doing them, I could not see the forest for the trees. I mean, I was so lost. And then at the end, he had some of these diagrams. I said, oh, yeah, that's what it's talking about. This is exactly what it's talking about. If you choose an epsilon, they chose 1.2. Divide 0.2 by 8, and you'll get, I guess, about this. is you within 0.025. Now, obviously, this is not drawn to scale, okay? Because if this is 0.2 up here, 0.025 would be much, much more narrow here. So they obviously haven't done this to scale, but you get the general idea. You know what else is it to scale? There's 27, there's 3. That's not the scale either, you know. So they've intentionally, that is not a slope of 8. That looks more like a slope of 1.5. So obviously they've expanded the y scale and expanded the x scale and condensed the y scale. So they're making it look pretty, but yeah, this is exactly what it's saying. If your y's are within 0.2, get your x within 0.025, you got it knocked every time for this problem. Okay, so that's example 1. Does that make sense? Oh, I forgot the B part. Find the values of delta that work for epsilon equal 0.2. They just did that one here. Let's do it for 0.001. Whoa, don't have to come out of there. Epsilon equals 0.001. Sorry, I didn't realize this was this one. What delta would you need? What do we do? Divide it by 8. Remember when we did the problem? Delta would be epsilon divided by 8. So take the 0.001 and divide that by 8. 0.0000125. Is that right? Punch it in and see. 0.001 divided by 8. (1.25) times 10 to the minus 4. Yeah, that's it. That's 1, 2, 3, 1, 2, 5. Yeah, that's it. All right. Once you do it for 1, you can throw any epsilon in there. You can find out the delta you'll need. Make sure delta's less than that. You got it knocked. And they do that in the text as well, but they don't have the picture for that one. They just show the picture for the 0.2. All right, ready to go to example 2. I'm real tempted to do it here, and then we'll go to, here's example 2. That's example 1, here's example 2. Prove that the limit as x approaches 2 of x squared, what would you say that was going to be? 4. Okay, we need to prove that. Okay, then how we prove it is let epsilon be some small positive number greater than 0. Then, or such that, such that the colon or the line there means such that absolute value of f of x, which is your x squared, minus 4 is less than epsilon. The epsilon would be greater than 0, such that that's true. Then that implies there is a delta greater than 0, such that 0 is less than x minus 2, absolute value of x minus 2, and that's less than delta. Okay? That's what we're trying to prove. Now, this is a little bit stranger. The linear ones have worked out so very nicely. Okay? Quadratics and higher, don't do as well, okay? You have to do a lot more fudging and manipulating and trying different things. But here's what we're going to do. We're going to take this and say, that's the same as x plus 2 times x minus 2. That less than delta. Okay? We just factored that. Well, guess what? We've already got an x minus 2 there. If we could only deal with what that x plus 2 is going to turn out being, then we'll be, okay, we can find out what our delta would need to be in terms of epsilon. Now, how do you do that? Okay? This is more difficult than the previous example because the gap is not a constant multiple of x plus 2. So here's how you proceed, and I actually put them together, they split them apart. X plus 2 times x minus 2. That product is also got to be less than epsilon, obviously, right? If the absolute value of the product is less than epsilon, that's also the product of the absolute values has got to be less than epsilon. Okay? So that's the first thing they did. Now again, you're awfully close to what you need. So what we're going to do, and this is always seems strange to me, because we're going to require the absolute value of x minus 2 be small, we may as well assume from the outset that the absolute value of x minus 2 has to be less than 1. So we want this to be small, so let's say absolute value of x minus 2 has to be less than 1. Now that's not very small, is it? Okay? But certainly if you're going to get smaller than that, it's got to be less than 1, right? So they just pick that value. Okay? This is a trick. Okay? It just seems to work. Okay? So that means, for that to be true, absolute value of this less than 1, what that means is negative 1 is less than x minus 2 is less than 1. I mean, that's what absolute value means, right? If the absolute value of the thing in there is less than 1, that means its positive value is less than 1, but the negative value has to be greater than negative 1, right? That's what absolute value means. Okay, so we got that. Well, what's the next step? Add 2 to all three sides of that. That's good to do with inequalities because adding or subtracting positive or negative numbers doesn't change the signs of that. So this becomes 1 less than x less than 3. Okay? Not a very big, I mean, that's a pretty big range of x. Okay? But you know it's got to be within that. Okay? Seems like, what's that? Say that one more time.
Okay, so you can take the 8 plus 2.
Okay. I think what you're saying is, yeah, you're wanting this thing to be less than 0. That's what we're aiming for. So why are we taking this one and making it something else? You'll just have to see. It seems like to me you should have taken this and made that arbitrarily small. Then you could have gotten this within some value. But let's see how they do it. It's sort of a backward way to me of thinking of it. But here's what they do. So they've done that. So we know the x has to be between 1 and 3. Oh, okay. We want this to be arbitrarily small. How small is small? Well, say again. Yeah, like 0.1 or something like that. Well, if it's less than 0.1, it's certainly less than 1, right? So they just chose that 1. They just picked it out of the air. A small number, but not really all that small. Yeah, it's got to be between, you can't say it's equal to 0 because remember, the x may not be defined at 2. So we can't say it's 0, so don't go there. But just pick another number, like 1. Okay, it's not very small, but you know we want it at least that small or smaller. Okay? So if that's the case, that means x has to be somewhere between 1 and 3. Got to be between that, period. Okay? And that's a lot of range there. Okay? We're going to try to narrow that down some. So
they have chose 1 and 2, or they just have to choose 3.
okay. You mean you wanted to choose something less than 1? You could have. But 1's such an easy number. Anything less than 1, say again? Yeah. You see, here we just said it has to be less than delta. Right now we're saying, let's say delta has to be less than 1. If it's less than 1, then this thing also has to be less than 1. They just chose 1 because they couldn't choose 0 because you can't say it's equal to 0. Okay? So, what's the next simplest integer? Smallest integer is 1. So they just pulled that out of the air, 1. So now that just defines x has to be somewhere between 1 and 3. It can't be any less than 1, and we sure don't want it any greater than 3. Okay? So let's just be satisfied that it's got to be within that range. Okay? Now what do we do with that? Okay? Well, let's go back to the other part here. If 1 is less than x is less than 3, then 1 is less than, okay. Back off here. Okay. This sounds, I mean, even to me, it feels stupid to do this, but this is how they do it. I keep hitting the wrong thing. Okay, there we go. Okay. Let's now do 1 plus 2 is less than x plus 2 is less than 3 plus 2, right? Now you might say, why did you do that? Well, that was for this part of it. Okay, so this is saying 3 has to be less than x plus 2, and that's less than 5. So your x plus 2 has to be between 3 and 5. Okay. So we got the x plus 2 between 3 and 5, and the x minus 2, that's less than 1. Okay? That doesn't seem like we're getting very far. Okay? But once we've got this, now we can go back and multiply this, and what we're not going to do, we're not going to worry about the lower part anymore. We're just going to deal with the upper part here. If we can guarantee that, okay? So what we've got up here, we've got this thing less than 1, okay? Down here we've got the x plus 2 is less than 5. Absolute value of x plus 2 is less than 5 from here, okay? Now the product of these two. That would be the absolute value, well, x plus the absolute value of x plus 2 is 5 times absolute value of x minus 2 is less than epsilon, right? Well, what do we do? Divide both sides by 5. Okay. Right? No. In fact, the only reason we got the x by itself is so we could add 2 to it to get that side. That's why we started the one we were really gunning for. Find out the limit on x so we can then add 2 to it so we can get the side we're looking for. And this tells us this, the absolute value of this is less than 5. Don't even worry about the 3. Less than 5. Now we have the absolute value of this is less than 5. Absolute value of that is just absolute value of that. And that's less than epsilon. So whatever epsilon you choose now, divide it by 5, and you guarantee that absolute value of x minus 2 is less than epsilon over 5. That's your delta. Okay? So now you can make that epsilon much smaller. Give me a small value. 0.25. Take the 0.25 and divide it by 5. 0.05, right? Okay. There's your delta. Okay.
So we don't do sine.
What's that?
So how do we know what's to when to use sine?
Okay. Yeah. You mean the SIG in science? You know, is that what you mean?
The SIG is sine, what she told me that the science inside the problem.
My hearing you so bad, I'm not thinking all of what you're saying.
I was asking when do I know when to use sine to do the sine?
The SIG in science?
No, the SIG is sine.
Oh. Well, this one doesn't have a sign with it.
This one is sine.
Oh, I see. That's what you were saying. Okay, I can't hear what either of you were saying. That was the earlier problem. That was the sine x over x. Here is this problem here. There's no sign, SIN sign in this one, so we don't worry about it. But this gives you a value for delta. No matter what epsilon you choose then, you can divide it by 5, and that's going to guarantee that you'll get within that. So let's try it. Oh, a Y chromosome did show up. Okay. Rodney's here. Still missing Richard, though. He was sick last week. I wonder if he still is. I don't know. I hear there's flus going around these days. Have y'all heard that? I saw it in the paper that there's a fair amount of it. What's that? Yeah, a lot of respiratory infections. Yeah. What's that? Is Richard sick, you say? Okay. All right. So this is then gives you that. Now, it's sort of a weird way to go about doing it, but it works. Basically, when you have a product like this, and one of the products is the thing you're looking for, that's what you start with, and just pick an arbitrary value. 1 is as nice as any. It's a small integer, smallest integer you can get. You can't go to 0, so go to 1. And then figure out what the x plus 2, solve that for x by doing your rule for absolute value there. And then get down to what x is. Then add the 2 to that so you can get the one that you don't want in there. And say that's less than 5. So once you've determined that, instead of absolute value of x plus 2, put 5. Okay? Then 5 times that has got to be less than epsilon, divided by 5. That's going to more than get you what you need. Okay? In fact, let's try one. Give me an epsilon. Pick it. Did you say 0.25 earlier? Say again? Do 0.4? Is that what you say? Okay. Let's have an epsilon of 0.4. Let's divide that by 5. Okay? And that's going to be 0.08, right? Okay? So, that's going to be 0.08. That's going to be your delta. Okay? That's going to be the delta, 0.08. So, let's do a 2.08 squared
0.264.
Okay, so for your epsilon of 0.4, you said you're well within that, aren't you? Okay. Way less than that. Okay, so yeah, you're in good shape there. So whatever you choose, whatever epsilon you choose, divide by 5. That gives you delta. Plug that in here. You're guaranteed to come within the epsilon of the 4. Okay. Then that's whatever I said. Rodney must not have liked it, so he left already. Okay. Now, let's see. Here is that problem that we were just doing. Let's see if anything they do or any way they do or any way they state. Their slides are so sketchy. Not much of them. So they started off with the absolute value of your alpha of x minus the L. What that is. We saw that was equal to absolute value of x plus 2 times absolute value of x minus 2. Actually, we want to say that's probably less than, but we'll leave it equal. Okay? Now, by choosing just out of the air that let x be the epsilon less than 1 and plugging it into this one, okay, that means 1 is less than x is less than 3. Then that means absolute value of x is less than 3. Add 2 to that, and you get 5. Well, I'm sorry. Then add 2 to all three sides. 3 is less than x plus 2 is less than 5. That gives you x plus 2. Absolute value of x plus 2 has to be less than 5. So put that in its place, and then that gives you your this is your epsilon. This is your delta, basically. So this divided by 5 gives you your delta. Okay. They skipped a lot of stuff at the beginning and skipped a lot at the end, but that's what you get down to. Now here's what that graph looks like. Okay? With that function there. Okay? Here's the graph, alpha of x equal x squared. Now you can choose a delta such that the alpha of x lies within epsilon of 4. Okay? Wow, that's a big one. Okay? No, lies within epsilon units of 4. Okay? Not epsilon of 4, lies within epsilon of 4. For all x's in 2 minus delta to 2 plus delta. You see, here's your 2, x is approaching 2, it's going to be within delta of that. So within 2 minus delta to 2 plus delta. And that's why when you gave me 0.4 for the epsilon, I divided by 5, and then I just added it to, we could have subtracted from it, we would still be within that. Okay? Then, but this is what your rule says. For any epsilon greater than 0, then you'll be within this band of 4 minus epsilon and 4 plus epsilon, as long as you choose a delta that's between, and the delta we chose was delta epsilon over 5, you choose that here, then you're guaranteed to be within this epsilon table. So, that's what this is illustrating for us. Okay. Now, fortunately, we don't have to use the formal definition much. Okay. What we do at the very beginning was figure the limit. That's mostly what we have to do. All right. Here's another level of complexity. Okay. Okay, this continues what we were just looking at. Sorry. I thought they were through with that. They're not. So here are the values we'll use. Absolute value x squared minus 4 less than epsilon, and then we went through that process to get down. If there is a delta such that that's the value of x minus 2 is between 0 and delta, where delta is the smaller of, here was the other part. Delta is the smaller of epsilon divided by 5 or 1. Remember, we chose epsilon less than 1. And I just was assuming we were only epsilon's less than that, so then for anything less than that, epsilon divided by 5. But even if you chose an epsilon of 6, then I wouldn't use this. I would use this one. Because we already said it had to be less than 1. So that carries for this. Most of the time, the epsilon is going to be considerably less than 1, so choose epsilon over 5. Or considerably less than 6, okay? Or even 5.1, choose smaller ones, and then you would always get it if you did that. Okay. All right. Let's do example 3. Prove that the limit as x approaches 3 of 1 over x, what do you think that's going to be? 1/3. You're absolutely right. Okay? Now let's do our formal definition there. This is true if for any epsilon greater than 0, there exists a delta between 0 and no, delta greater than 0. We don't need it, a limit on the upper side yet. There is a delta. Let's see, I've got it. For any epsilon greater than 0, such that, this is where I left off, the absolute value of f of x, which is 1 over x, minus your limit, 1 over 3, is less than epsilon. Let's see. I've said it right. If that, there is a delta. I had it right. There is a delta between 0 and 1 such that that's true for all that's an epsilon. That's sort of ugly. Let me write that better. Okay. This is epsilon. Okay. For every delta 0 less than there is a delta greater less than. I said I've got these symbols backwards. Sorry about that. There is a delta greater than 0. I had it right, but you don't have to say less than 1. Delta greater than 0, such that the x minus 3, the difference of this is less than delta. You're guaranteed to that. So for any epsilon greater than 0, there exists a delta greater than 0, such that the absolute value of the f of x minus L less than epsilon anytime the x minus 3 is less than delta. Okay. Now, this one we got more mess to do. Let's start with the function. Okay? Remembering what we're trying to get to. Okay? So this function here, obviously, before you can subtract fractional forms, what do you have to have? For you to subtract fractional forms, what do you have to have? Common denominator. What would it be in this case? 3x, right? okay? To make this be a 3x, you multiply the numerator by 3. To make this by a 3x, you multiply the numerator by x, right? So this gives us 3 minus x over 3x, less than epsilon. All right. We're fairly close. That 3 minus x is, that's pretty close to x minus 3, especially in the absolute values. And I did leave off the absolute value there. That has to be an absolute value there, sorry. We've got it because 3 minus x, x minus 3, and absolute values there are the same. Okay? So, my temptation here would be, let's pick a value. They rewrite this one more time, and because absolute value of x minus 3 and 3 minus x are the same, that's the absolute value of x minus 3, but preceded that, or postceded it, or wherever, 1 over 3x. Okay, they rewrote it like this, and that's less than epsilon. Okay. Now, why they're not putting in that, I don't know, but it is that. Now, we want this to be small. Okay. Now, how small? And again, we're going to go back and do something very similar to what we did before. Let's say the absolute value of x minus 3, we want to be less than 1. Okay. We don't want to choose 0 because you can't be 0. So let's just stick with integers. They're nice to deal with. So the next smallest integer is 1. Okay? That's our condition. So what does that mean? Negative 1 is less than x minus 3 is less than 1. Right? That's what absolute value means. That value is in between minus 1 and plus 1, for its absolute value to be less than 1. And now let's add 3 to both sides. Looks familiar, doesn't it? I mean, all 3 sides. This will be 2 is less than x is less than 4. Okay. Now, if we chose, now, and what we're trying to do is get rid of this one, right? Okay? If we chose x to be 2, then that would be 1 over 6. If we chose x to be 4, that would be 1 over 12, right? 1 over 6 is greater than 1 over 12. So this time we're going with the less because we want to make sure we're going to be less than this, okay? So this time we're not going, before we went with the bigger number, because this is reciprocal, this produces the bigger number. So we want to make sure we're less than that, okay? So, we go back here, we'll choose the 2, plug this in here, and this will be absolute value of x minus 3 times absolute value of 1 over 6. Well, 1/6, you don't need the absolute value signs anymore. That's always positive. So that's going to be 1/6. And that's less than epsilon. Okay? Well, what we want is this situation here. So what we're going to do is multiply 6 here and 6 here. So now we get absolute value of x minus 3 is less than 6 epsilon. Okay? Oh, because this is reciprocal, you really don't have to be as close to v in between that. This is going to do. So give me an epsilon, as small an epsilon as you want. 0.45? Okay? 0.45. That's less than 1, so we're okay there. We're going to stay with that. 6 times 0.45 is going to be, oh boy, 20,
2.77.
so again,
2.7.
2.7, okay? So that's going to be 2.7, okay? And if you give me a delta, and this is going to be your delta, of 2.7, okay? So delta of 2.7. So x could either be 0.3 or minus 0.3, okay? Okay. Yeah. Let's see. Getting kind of crossed up with what I'm going to do. So let's put that in there. A 0.3. 1 divided by 0.3 is? 1 divided by 0.3 would be 3.36. Say that? 3.3. Okay. It's 3.3, right? 3.32333. Say that, yeah. Oh, 3030. Okay. You said repeating. I couldn't understand what you said. Okay. Okay. Let's see where we began this. I said for any epsilon greater than 0, you chose, what did you choose? 0.45? No. Yeah, 0.45. For any epsilon 0.45, okay? Then, if that's only as close as you want to get, you can have a delta of up to 2.7, which would be this. And when you did that, and put that value in 0.3, you're going to get 0.3030, which is within the 0.45 that you first said. Yeah. So sure enough, that works. It's a big number. So it's either going to be, the delta is either going to be 6 epsilon or 1. Oh, yeah, 1. Because we wanted the delta to be less than 1. Whichever is less, okay? And actually, if you chose the epsilon to be 0.45, then I would choose my delta to be 1 because you're less than the other. So yeah, that works, okay? The delta would be 6 epsilon. Okay. Now, let's see how they go with it. And it's a lot like we did. This is what you want. F of x minus 1/3. This is the function minus the limit. The function here was 1 over x, and the limit was 1/3. And they did the same thing we did. 3 minus x over 3x. You got least common denominator, we got that. That's 1 absolute value of 1 over 3x times the absolute value of this. It doesn't matter. The absolute value, you can switch to subtraction. It doesn't matter. Then you chose an x, a delta less than 1, and that made, if you plug that in here, that means minus 1 is less than x minus 3 less than 1. Add 3 to all 3 sides of that, and you get 2 is less than x is less than 6. Okay? Now, you choose the smaller of what this would be. 1 over 6, the larger, 1 over 6 or 1 over 12. 1 over 6 is largest, so choose that, and then you have that. That then has got to be, well, if I shrink it. That's got to be less than delta. I mean, that's your epsilon. Okay. Somewhere up there you said epsilon. Is the functional value, which is what this was. This has to be less than epsilon, that less than epsilon, this less than epsilon, this has to be less than epsilon. But here is your delta that we haven't written here, but they haven't written. We did multiply that, and you got 6 times epsilon will have to be your delta. Okay? Here's where they do the second part. And again, the book's presentation of it, they do things in sort of a strange presentation, but here we go back to this less than epsilon. If that's less than delta, where delta is the smaller of 1, that's where we started, having that equal 1, less than 1, or 6 epsilon. So whichever it is, whichever delta is smaller than either 6 epsilon or 1. When y'all chose the epsilon of 0.45, 6 epsilon was greater than 1, so we chose 1. Okay? If you had chosen a smaller epsilon, like 0.03 or something like that, then that would have been 0.18. You would choose that as your delta. So it's the lesser of those two. And since you chose the 0.45 for your epsilon, that gave us 2.7 that's greater than 1. We would have chosen a delta of 1. That guarantees you're going to be within that easily. Okay. And that's the next part. Okay, you got to go. We're not going. See, how are we doing on time? Well, we don't have much time. Oh, we're so close. If you have to go, what I'm going to do, we're going to cover just a little bit more. This probably won't finish this until next time, but I thought just to give you a little head start on it, here's your test. For chapter 2. Okay? And we'll probably finish the chapter actually next time, so the test won't be due any sooner than a week from Thursday. If you finish it sooner, I'll take it, but that gives you a couple of days to ask me questions. Okay? Remember, I'll answer any question to clarify a question on the test, but how to work a question on the test, I won't do it. But if you find anything in the book, I'll work those in the book that are similar to the ones on the test. Okay. All right. So that's where we ended that one. Now, how does it, this is a different problem. Okay, they didn't show the graph for the 1 over x. Okay, you could draw that yourself if you wanted to. But this is your graphical insight. Keep the graphical interpretation of the limits in mind. Figure 4a, let me blow this up a little bit. In the a part here, f of x is approaching L. Okay? Your f of x function here is approaching this limit L when x is approaching c. Okay? That's what it sure looks like to me. The function is continuous at c, therefore taking delta sufficiently small, you can make the gap smaller than epsilon because it's continuous. All you have to do, if this is your epsilon gap, L plus epsilon to L minus epsilon up here, then all you have to do is reduce this until these values are in there. Okay. However, if the function is not continuous at x equals c, and it's not a removable discontinuity, if it's a removable discontinuity, no sweat, we did that earlier. But if it's not a removable, like a gap discontinuity, what are we going to do with that? Okay? If you choose an epsilon in here, okay, if your function is going to a as x approaches c from the left-hand side is according to B as X is approaching C from the right-hand side, and you have a big gap in there, I can give you an epsilon in here. You'll never, ever, ever get close enough, because these two, the closer you get, that gap still goes there. So if your epsilon is out here or here, no problem. But if you choose an epsilon in here, there's no way you'll ever get a value delta that will make that. So it's not going to work. So obviously that doesn't have a limit as X is approaching C. This one, yeah, it's a continuous function. Surely it does. Okay? You can get as close as you want to. All right. Now, here is the sentence that saves you. Okay? Besides saying we're out of time. I guess we'll just pick up there next time. Because we do end at 11:10, right? Okay. We got started late, sorry, Rodney, because I went down the hall. I don't even remember why now. Oh, to make copies of your test. Okay? And I came out and I decided to go to my office because I wasn't able to eat breakfast this morning. When I was in the shower this morning, my wife came in and said, the dog's cutting up this morning. I don't know why she's doing this. I said she must have heard me that I was up. But when I went downstairs, I found out that wasn't the reason. She had gotten really, really sick in her bed. And so I went downstairs and had to clean her bed, clean the cage, clean the floor around the cage, and it was a mess. So I didn't get to eat breakfast. So I grabbed a granola bar after I got here, and I thought, well, let me go get something to drink too out of my office. And when I went down to go to my office, and this adjunct instructor who's now next door was there, she said, I can't get the projector to work in 2:59. So I spent time with her, then found somebody to work on it and stuff like this. Came up here and I was close to 15 minutes late. So if we'd have had that 15 minutes, we would have gotten this, but it doesn't matter. Homework exercises here. Do any of the odds 1 through, I've assigned these before, but I can't find where I left off. Any of the odds 1 through, maybe I didn't assign these before. No, I guess this is the first time we've been in there. Wow. I say any of the odds 1 through 17, okay? I would do some of each of those. You know, don't just do one and say that's enough. Then do some of the odds 19 to 23, and then do some of the odds 25 to 29. Now, if you can't do those at the very end, we will do a little bit more improving the limit theorems. But as soon as we finish that, and I'll give y'all your test too, so you can get a head start on it, and we will go from there. So let me pass these out to you, or just pass out one. That's one. Richard is the one. All right. We will go from there. So Richard, if you're listening to this, come by and get your test. Okay. Why this showed up here. Okay. So we'll end that. Yeah. It's supposed to be an hour, and how long is the class supposed to go? Wait a minute. No, that's right. Yeah, we got started late.